Good afternoon and welcome to the University of Toronto Physics Colloquium. My name is Sajeev John and I'll be the moderator today. Let me just remind the audience that questions can be typed within the Q&A tab, or if you prefer to use audio, you can use the raise hand function at the end of the talk. So it's my distinct pleasure today to welcome our speaker, Professor Jelena Vuckovic. She's currently a professor and the chair of the Department of Electrical Engineering at Stanford University. Jelena completed her undergraduate degree in Serbia before coming to Caltech, where she did her PhD with Professor Axel Scherer in the field of photonic crystals. Jelena then moved to Stanford, first as a postdoc in applied physics, before being appointed the following year as a faculty member in electrical engineering. She's a fellow of the American Physical Society, the Optical Society of America, and a fellow of the IEEE. She's also the 2019 recipient of the Arthur Frank Harvey International Research Prize. I first met Jelena about 12 years ago at a photonic crystal conference in Sydney, Australia. So Jelena, we're delighted you could join us today. And with that, let me turn things over to you.
Well, thank you very much, Sajeev, for your kind introduction. And thank you also for your invitation. It's really a great pleasure and honor to give this colloquium. And as you heard from Sajeev, actually, my PhD thesis was on photonic crystals, which were pioneered by Sajeev. And a lot of my work revolved around the ideas, his pioneering ideas on cavity QED and photonic crystals and so on. So it's a really a great honor to be here and be able to speak to you virtually this time. And I will talk about my group's recent efforts on classical and quantum photonic systems. I will address both directions. I know, of course, there is a lot of beautiful research at University of Toronto in both of these areas. And of course, the common theme are scalable photonic structures that enable a lot of these exciting applications and experiments that we're working on. So let me just start, for those of you who are maybe not working on photonics, with this slide summarizing some of the exciting applications of photonics that many people are working on today. And they include optical connections for data centers, for computers, optical computing platforms, such as optical neural networks, quantum photonic processors in quantum networks, augmented reality glasses, variety of sensors, biosensors, and also sensors for autonomous driving for LiDAR systems, for example. So all these are a variety of applications for photonic circuits that many groups around the world, including ours, are interested in. But as you can already guess by looking at this slide, even if you are not really working on photonic systems, is that for implementation of pretty much all of these applications, you really need integrated photonics. Free space optical solutions, like the one shown on the left from my lab, are not really going to be applicable to something like augmented reality glasses, where you really need to pack a lot of optical devices into a small footprint that someone can carry around in the footprint of their glasses. So how do we do that? Well, of course, for several decades, people have been working on integrated photonics. And these are some of the pictures of pretty traditional integrated photonic elements in silicon photonics, such as resonators and filters and grating couplers. But there are actually problems with state-of-the-art photonics, or kind of these mainstream photonics that people have been pursuing for decades. And first problem is that a lot of these components are bulky. They occupy tens of micrometers per component, and you can't really miniaturize a lot of photonic elements to something on the size of electronic components, but there is also no reason why many of these components have to be so large, as you'll see in a moment. The other problem is that many of them are very sensitive to fabrication errors, temperature variations, which is why people often integrate a lot of tuning elements like heaters. You see that here, in order to tune everything on resonance with each other so that they can have a functional circuit. And that's, of course, very problematic, because when you're building a large system consisting of thousands or hopefully millions or even billions of components, it's very difficult to have all of these knobs necessary to tweak every individual component. Also, a lot of these elements are designed by manual tuning of a few design parameters, which means that there is no reason to believe that they are optimal. We also have limited functionalities. For some of the new applications, we really need new designs, and there are no off-the-shelf designs that would be useful in that context. I'll show you some examples today. Finally, in many cases, as a result of all this kind of brute force design process, many elements are lossy. You have something on the order of 50% efficiency in a coupler that is supposed to couple laser signal to the chip. And while that's okay for some classical applications, it's still not good because you're wasting 50% of the input power. And certainly it's not really good for quantum applications where you really cannot really tolerate losses of that magnitude. And that's really the reason why we've been thinking in my group for about 15 years now on about a different approach to designing photonics, which we call inverse design photonics. And by inverse design photonics, we mean start from what function you would like to have in a certain element, what mapping between input and output you would like to have, and then efficiently search through the whole parameter space of fabricable structures until you find the optimal one that it satisfies that mapping between input and output. And that mapping is not really the only thing that we characterize in the design process. We also include efficiency. We also include robustness to environmental variations, fabrication errors, temperature, anything that we find important to build functional systems. So this process is basically efficient search of the whole parameter space, which means that it's a combination of fast optimization techniques and fast electromagnetic solvers. And we do all of this in 3 dimensions in order to capture the behavior of the system. And here you see some examples of the devices that we designed and demonstrated. This is the same one that's behind me. It's a wavelength splitter in a small block of silicon. Actually, this was made and demonstrated by my former PhD student, Alex Pigot, who prior to coming to my group had been a student at the University of Toronto. This is an on-chip particle accelerator. I'll mention that, it's described that a little bit later. This is another example, non-reciprocal pulse router. And this is just a piece of the inverse design circuit. I mean, for the past 5 years, we've been also working with major foundries on showing that inverse design is compatible with foundry-based fabrication, not just with the university fabrication facilities. And we've shown that this is possible. So I'll also give you some idea where we stand in that respect. So that's really what we've been working on. And although these structures that you see here are all based on silicon, on insulator, which is the mainstream photonic material, we've also shown devices in a variety of other materials, as you'll see later. And the approach is really material agnostic. So you can really apply this to any material you like, as long as you know fabrication constraints and material properties. And working on this for a long time, we developed a software suite, which we call SPINS, Stanford Photonics Inverse Design Software, which now many groups around the world are using, and actually software can be licensed from Stanford. But we also have a basic open source version, which we call SPINS-B, and this is available on GitHub, and a lot of people also use this basic version and play with it. So let me now give you the idea of how we're doing this. We started initially in experimental demonstrations by demonstrating kind of simple elements such as wavelength splitters and trying to show that things really work the way we designed them, and we would fabricate these elements in nanofabrication facility at Stanford. So these elements here are wavelength splitters. So these are designed to split 2 different wavelengths or 3 different wavelengths in a small footprint of 2.8 by 2.8 or 4 by 5 micrometers. And for those of you working on photonics, you know that typically people do these types of filtering functions with ring resonators, for example, that are much larger in footprint. So we wanted to do it in a smaller footprint with equally high efficiency as you would do it in wavelength division multiplexing systems. But we also wanted to show that this could be done in such a way that it's robust to typical fabrication errors, so that we didn't really have to include any tuning elements to tune transmission characteristics of different elements on resonances with each other. And we were successful in that. Actually, here on the right, you see demonstrations. So these are measured transmission characteristics for many different devices of this type, fabricated with the same parameters. And although our process is not perfect, we don't really need to tune any of these elements. When we measure transmission characteristics and plot them together on the same plot, they all line up on top of each other for both of these blocks. So that was really exciting for us. And that was really the beginning of the story in a practical sense. 10 years of computational work really preceded this. But once we saw these results, we were convinced that we could really use this towards a lot of practical applications. So now I'll use on-chip particle accelerator, which is really the ultimate kind of new application of photonics, to explain you the process of design. And our goal in this process is not just to make more robust devices, photonic devices with smaller footprint, but also to introduce and enable new functionalities. And really, on-chip laser-driven particle accelerator may be completely new functionality for photonics, in our opinion. The idea is pretty simple, and the idea is really something that my colleague Bob Bayer at Stanford has been working on for a couple of decades, inspired by really these images here. As you know, in traditional accelerators, people use microwaves, radio frequency waves to accelerate particles, and this is a Stanford linear accelerator, which is few miles long. But then if you, instead of these longer wavelength electromagnetic waves, you use infrared light, for example, then in principle, you should be able to scale everything down by a factor of about 10,000, which is the ratio of wavelengths. And that would also mean less expensive systems, more compact, and so on. So how do you do that, right? You can't really just take a typical linear accelerator and shrink everything by a factor of 10,000, because the microwave and radio frequency wave components would not really work. And instead, you have to redesign everything for infrared light. And you have to really rely on the electrics in the process to avoid losses. But that's not a trivial process. And before us joining this team of Bob Bayer and collaborators, try to use a variety of photonic crystal, three-dimensional photonic crystals, two-dimensional photonic crystals to demonstrate on-chip particle accelerators. And they were actually successful in that process, but they could never really get to the configuration that would be scalable and that could be actually completely done on a chip. Which is why we decided to approach the problem in a different way, to really approach it as an inverse design problem, and design stage of accelerator as an inverse design problem, where we are basically trying to maximize acceleration gradient for particles that are coupled to the structure. Right, so we're designing this permittivity distribution in such a way that for a laser light at a particular wavelength, 2 micrometer wavelength in this case, the structure has such a permittivity distribution that electromagnetic field inside of the vacuum channel would always be in phase with the electron, with a particular energy that's coming here and propagating through this structure, so that electron always gets a kick in the right direction and it's always accelerated, never decelerated. And that's really what we did. And you see that here for this stage of accelerator, we actually have a photonic crystal periodic structure, but then next stage, as an electron is getting accelerated, would actually have a different periodicity and different features. And here, when you couple light on a side, you see here electromagnetic field distribution. So for an incoming electron, it would always be in phase with electric field, and it will always get accelerated. So once we designed it, we fabricated it in silicon for incoming laser with 2 micron wavelength. So this is 300 femtosecond pulse laser. We also inverse designed these couplers so that they have a large bandwidth, so that they could couple these very short pulses without loss, and also not melt, because this is a very energetic pulse. Laser beam would propagate here, get coupled to this structure. Electrons with 83.4 kilo electron volt energies are coupled to the vacuum channel, and then we characterize them at the output. And again, this is just a single stage in a real accelerator. Like in traditional accelerators, you have to cascade hundreds or thousands of these stages to reach useful energies of electron. And structure is 30 micrometers long for a single stage. So again, when you look at this, even if you imagine having a few hundreds of stages in order, which would be necessary to reach useful energies, it would still be something on the order of few inches on a chip. right? So even 1,000 stages is just a couple of inches on a silicon chip, which is completely doable. And it would be a large reduction in size relative to accelerators that are a few miles long at least. So we built this and characterized and measured 30 mega electron volts per meter acceleration gradient in this stage, which is actually already on par with some of the used accelerators today. So the experiment, just outlined here, is very simple. We couple electrons here. We measure their energy at the output. When there is no laser beam that is coupled to the structures, electrons enter and exit with the same energy. And when there is a light coupled to the structure, then the electrons are accelerated and they get about 1 kilo electron volt energy, additional energy within this 30 micrometer stage, which means 30 mega electron volts per meter acceleration. And if you had 1,000 stages, you would go from these 80 kilo electron volts to mega electron volt energy. And mega electron volt is already very useful for a lot of applications in medicine, for example, where you use it for irradiation of cancer patients or for some imaging applications and so on. So that's kind of the ultimate application. And that also tells you how we're designing really structures. And what we're trying to do now is, of course, cascade a lot of these stages so that we can build 1,000 stages on the same chip and get to those mega electron volt energies. And there we're actually working with commercial foundries because this is beyond complexity of fabrication that really we should rely on in our university nanofabrication facility. And for the past 5 years in general, we've been looking into this idea of using commercial foundries for fabrication of more complex inverse design circuits, because simply for functional systems, you need to integrate a lot of different elements. And we wanted to prove that approach of inverse design is compatible with foundry-based fabrication, because if it's restricted to university experimental fabrication facilities, then the yield or throughput of fabricated structures would not be sufficiently large. And we've been very successful in that process. And I'll just show you quickly some of the latest results. So these are structures fabricated in a commercial foundry, AMF in Singapore, but we also work with global foundries and many others. And this is optical interconnect system for computers. People already use optical connections in data centers between different servers to increase the communication speed and reduce energy consumption. But the other important part where we need to introduce optics is for communication between different processors and memory. So chip-to-chip communication in a computer, or even on-chip communication, because a lot of energy loss and a lot of limits in terms of communication speed for particular loss come from basically electrical connections in computing systems. And here we've shown that we could use optical connections to achieve terabit per second error-free communication between chips, two chips, or on the same chip. And this was fully fabricated in a foundry. And the way we could achieve this error-free communication without any error correction is by combining a traditional way of encoding information optically, which is wavelength division multiplexing, where you encode information for different end users in different frequencies. But then we combine that with mode division multiplexing, which means that you can multiply kind of each frequency channel with a certain number of modes to increase the total number of communication channels. So here we used 4 different modes, which means that everything is increased by a multiplicative factor of 4. And people have thought about mode division multiplexing for many years, but doing it in an on-chip configuration efficiently has always been a bottleneck, because people generally working with single mode waveguides and multi-mode waveguides or multi-mode systems don't have perfected elements for a splitting or a routing of different modes and so on. And that's exactly the problem that we addressed using inverse design. We designed this mode division multiplexer, demultiplexer, which is 6 by 6 micrometers large. And the role of this element is to route different input waveguides to different output modes, right? So these are modes with different output symmetry. And we can do that with very low loss and in a very large bandwidth of 100 nanometers, which is actually important for using a lot of different frequency channels. So you can see that design is very important. Our first generation of these multiplexers didn't really have such a low loss, and now the newer generation has extremely low loss and still the same foot rate. And then, we can actually implement different frequencies at the input using frequency comb. This is a silicon nitride-based microcomb made by Scott Papp's group at NIST, UC Boulder. This is the output of that comb. So you have a lot of frequency channels that you can use, and then you feed that into this interconnect system. And then we did these high-speed measurements with Peter Delfayette at the University of Central Florida in collaboration also with Perusa Flatuni, our collaborator from UPenn, and group of Alan Billner from USC as well, and John Bowers from UC Santa Barbara, David Miller from Stanford. It was actually a really large collaboration. And what we did here was measurement of the total communication rate, which is approaching terabit per second, and has extremely low error rate, 10 to minus 12, right? So it's like 1 in every 10 to 12 bits would be erroneous without any error correction. So that's actually extremely important for these practical systems, and we're quite excited about it. And we also showed that we could actually do it for chip-to-chip configuration by using specialized fibers made by Corning and our collaborator, Dan Maron from the Hebrew University of Jerusalem. So that's kind of how foundries can enable even practical systems for today's communication, optical communications in data centers or inside of a computer. But being a lab working on a variety of classical and quantum applications, and also looking at the limits of this inverse design, we also wanted to see whether we could design this in such a way, or whether we could implement elements to convert to a variety of different modes at the output. For example, can we make compact vortex beam emitters, which would produce different angular momentum modes at the output, which is, of course, something that people have looked into a lot, both for particle trapping, but also in the context of quantum communication for implementing hyperentanglement. And we showed that we could actually do this efficiently, and we could do it also in a broad wavelength range by using these compact elements, 3 by 3 micrometers. So this is something that you could use instead of a faceplate to generate particular vortex beam at the output. And here you can see how the output beam profile matches theoretical prediction for all of these different designed elements that would convert guided mode from silicon waveguide to a free space vortex beam at the output. And maybe most interestingly, you can kind of get another layer of complexity, where instead of just conversion to a particular vortex beam, you can multiplex different vortex beams. So design elements that multiplex different waveguide inputs from on-chip configuration, and then produce output, which basically is a superposition of different vortex beams. So if you excite it from the left, you have particular angular momentum in the vertical direction. If you're excited from the bottom, it's a different. If you excite it from the right, it's a different one. And then if you excite it from all directions, you will have a superposition of this. So that's another interesting thing you can do, and there are many more. So I'll just quickly show a few more examples. For example, optical phased arrays. This is maybe best described as optimization of photonic crystals. People have spent many years trying to engineer dispersion of photonic crystals for a variety of applications, which range from nonlinear optics to light matter interaction. But there is a limit to how well you can do that. You can't really draw dispersion relation between frequency and a wave vector and optimize kind of manually by brute force the structure so that you achieve that. But here we've shown that we could do it by this optimization approach, where we just let the computer search the whole parameter space until we achieve desired dispersion. And that was achieved here, and it enables beam steering at the output by 20 degrees in a 20 nanometer bandwidth. So it's really very large group index, slow group velocity in a large range of wavelengths, which would enable optical phased arrays that are much more compact and practical than kind of state of the art. So this is the optimized photonic crystal structure, and you see a lot of different elements that are kind of interfacing this photonic crystal circuit to the surrounding traditional silicon structures, and converting modes of traditional silicon waveguides to photonic crystal structures, and doing all the mode matching. And then when we implemented everything and fabricated, we measured this beam steering. So this beam steering is essentially dispersion of the structure, And you see that as you change the wavelength of the input laser by 20 nanometers, you have this linear dispersion regime, and you tune the output angle by 20 degrees. And to the best of our knowledge, this is kind of a record achieved beam steering at the output for minimum input wavelength range. So that is yet another application. And finally, the last one that I'd like to highlight, which is interesting for those of you who work, for example, on nonlinear optics or anything related to resonators and cavity QED, is that with this approach, you can also do dispersion engineering of microresonators. Designing a resonator itself, it's a relatively small parameter space. You know, you rely on total internal reflection or distributed Bragg reflection. People have really designed pretty good resonators manually already. But what is missing in the process of designing a resonator is coupling of that resonator to the surrounding exciting or coupling particular wavelengths, or controlling the dispersion of a resonator if you're using it for nonlinear optics applications, so that you can do some mode matching for nonlinear optics, or achieve a flat spectrum for frequency combs, or enable a variety of other applications. And we've shown that we could start from a traditional resonator, such as a ring resonator shown here, and insert these dispersion engineered elements, which are actually optimized. And these elements could really control the dispersion between, switch it to anomalous dispersion, for example, go for counter propagating and directly propagating modes to different dispersion regimes, which would actually be very important for frequency combs or for nonlinear optics. This could also be done in Fabry Perot resonator geometry, where instead of inserting this element that would affect differently propagating modes in a ring resonator, you could do the same thing by designing mirrors of a Fabry Perot resonator so that they have a particular phase response for each frequency. And we've shown that also here. And of course, you do all of that with still very high Q factors. We've also shown that we could kind of obtain, use the multi-mode waveguide, which has much smaller propagation loss in an on-chip configuration because it's significantly wider. We could use that for the body of the resonator, and then use these engineered mirrors outside to couple this outside to the single mode waveguides that are normally used in photonic circuits. And that enabled us to experimentally increase the Q factor of these silicon resonators from 500,000 to about 2 million, right? Because we are relying on much lower propagation loss waveguides in the body of the resonator. And many other things. So clearly you can augment the functionality of a resonator or build much better resonators for a variety of applications once you rely also on these inverse design approaches for their coupling to the environment or for their engineering, dispersion engineering. So that gives you an overview of inverse design approach. And of course, everything that I showed so far was pretty much classical in applications, but photonics is also very important for pretty much all of the quantum applications, or some sort of electromagnetic wave propagation is important for pretty much all of the quantum applications, which is what I would like to actually spend the rest of my talk talking particularly about that aspect of our work. And in my group, we work on semiconductor systems. I talked a lot about silicon, but we also work with a variety of other materials, and we're interested in building functional photonic systems, both for classical applications such as optical interconnects or LiDAR, as I mentioned, but also for quantum applications. And I'm sure that you're all familiar with a lot of exciting developments on building functional quantum systems in superconducting circuits, in atomic physics systems. And of course, there is a lot of beautiful work on that at University of Toronto as well. But we are actually working on semiconductor-based systems, right? So we're actually trying to make really miniaturized version of these systems that would rely on semiconductor chips. So how do we do that? And why do we do that? Well, clearly, some of the infrastructure can be removed from around the chip because we don't really need to trap an atom. Our atoms would already be trapped sort of in the environment. We still need some lasers and the detectors around, but we think that this could be a more practical configuration for some of the applications and maybe even more scalable down the road. So now going back to quantum technologies, there are many different There are actually 4 different pillars of quantum systems or quantum technologies that people are interested in and working on. I mentioned quantum computing, quantum simulators. Of course, there is also a lot of work on quantum sensors and quantum repeaters and networks, and these are some of the state-of-the-art proposals or demonstrations on all these platforms. And some of the platforms that people are working on are more suitable for some of these applications than others. For example, superconducting circuits are not really very useful for quantum networks because they're not directly interfaceable to optical photons, so you can't really connect them long distances. Although people are really working on it very, very actively. But in reality, if you have a system where you have homogeneous long-lived qubits with good optical interfaces so that you can entangle large numbers of them, and if you have efficient optical connections, you could use the same platform to implement all of these different technologies. And the platform that we're working on, which are impurities in semiconductors, has been actively used in some of the state-of-the-art quantum sensors and also state-of-the-art quantum network, 3-node quantum network demonstrated by Ron Hassan and Stephanie Wenner at Delft. But we're actually also actively working on investigating whether this is also useful in the context of building solid-state simulators and computers. So what is our platform of choice? For us, platform of choice is really an artificial atom, impurity in a semiconductor, and then we engineer and carve photonic structure around it. So for example, here you see impurity in diamond, and it's really like a naturally trapped atom in a solid state environment. And for those of you doing atomic cavity QED, this is very similar to atomic cavity QED systems, except that you don't really need to trap an atom. It is not in vacuum, it's in basically the solid state environment, and then you engineer mirrors and photonic structure around it. But in terms of physics, is also very similar to many other platforms, for example, circuit QED, where you have this engineered dipole Josephson junction inside of a microwave resonator. So you can study same type of quantum optics in a microwave regime in that particular case, like the same one that we're studying in the optical regime. So why are we interested and excited about this particular platform of color centers in semiconductors, such as diamond and silicon carbide? First, you're working with semiconductors. Silicon carbide, as I'll tell you later, is a pretty commonly used semiconductor, used also in power electronics, and it's very readily available. These systems can also operate at somewhat elevated temperatures, few Kelvin, which simplifies things if you were building a quantum network and distributing nodes every few tens of kilometers. They already have excellent optical interfaces, which is, of course, very important for quantum networks or construction of quantum transducers that would interconnect superconducting systems. And for some of these elements, also the quantum memories time or storage time is actually even better for some of the leading platforms. So number of 2-qubit gate operations that you can perform per spin qubit time in the material is actually even better than for superconducting qubits, because operations are very fast and the storage time is comparable in terms of the coherence time. So that's quite exciting, but of course, elements are smaller by a factor of about 1,000 relative to superconducting circuits, and you have to rely on novel nanofabrication techniques, ion implantation, growth, so on. You really literally have to insert these impurities at the desired positions with minimal damage to the lattice, as opposed to superconducting circuits where you define everything lithographically. So of course, the technological challenges are much larger, and that leads to a lot of inhomogeneities in the system that we've been trying to address over the years. So for us, the choice of these spin qubits, and we work really on optically controllable spin qubits, are spin qubits in impurities in diamond, such as silicon vacancy and tin vacancy color centers in diamond. And they're essentially 2 missing carbon atoms and 1 silicon or tin atom embedded in between. And a lot of effort has been done by our group and many other groups on silicon vacancies in diamond, including excellent quantum photonic interfaces and also 2-qubit interaction with the same cavity at Harvard. Tin vacancy in diamond is a more recent color center that we and others have been looking into, and we're more excited about tin vacancies than silicon vacancies because you can achieve pretty much all of the advantages of silicon vacancies, embed them in the good photonic structures, have good coherence time, but even at slightly elevated temperatures, you don't really need to put them in dilution refrigerator as you need to do with silicon vacancies. And also you have higher internal quantum efficiency to begin with, which is also very important. So recently we demonstrated quantum photonic interface for thin vacancy in diamond, which means we kind of really coupled this artificial atom to a single mode of the cavity. And also at the same time, there was a very exciting work in collaboration between the group of Meta Tature in Cambridge, UK, and also Dirk England at MIT on demonstrating optical spin control for thin vacancy in diamond. And a little bit after our demonstration, the group of Marco Lancher at Harvard also demonstrated quantum photonic interface for this particular qubit. So this is a growing field and quite exciting, and a lot of groups are moving to thin for the reasons I already explained. So that's one set of kind of qubits that we're interested in. The other is qubits in silicon carbide. Silicon carbide is much cheaper than diamond, and that's why people use it in fake diamonds, in fake jewelry. It's also used in the abrasives, it's used in heating elements, power electronics, you can get it on 6-inch wafers, and people also use it in MEMS devices. And it hosts a lot of exciting color centers. We work on silicon vacancy, which is missing silicon atom in 4H polytype, but a lot of groups do work on these other types of color centers, and a lot of leading work has been done by the group of David Avshalom at the University of Chicago. So we have been interested in silicon vacancy and silicon carbide, and we've been doing a lot of work in collaboration with your Graftrap in Stuttgart because of the good spin coherence properties and convenient wavelength. And we've been looking into it for a number of years, but of course, once you develop the platform, it's applicable to other types of color centers. But as I said, right, coherence time is long. You can go to quantum memories, build quantum memories in principle with millisecond storage time. You can do operations with gigahertz speed, but there are problems, right? Why didn't this system scale to the scales of superconducting qubits or atomic quantum simulators or ion trap-based systems? And the main issue are inhomogeneities in these systems. And a lot of these inhomogeneities come from this the fact that you have to use very sophisticated methods to build these systems. They are so much smaller, and you have to really control individual atoms in a solid state structure, and that's really not a trivial process. So you encounter spatial inhomogeneities, meaning that it's difficult to insert these atoms at the desired positions with perfect yield, and also spectral inhomogeneities, which come from the fact that these atoms are not in vacuum, like neutral atoms in atomic cavity QED, or ions. Instead, they're in solid state environments, and any imperfection would lead to changes in the transition and shifts in the transitions, which for us in best case scenario are on the order of 30 gigahertz. So we spent a lot of time developing methods for both spectral tuning and compensation of spatial inhomogeneities in order to be able to build scalable systems. So at the moment, what we're doing for addressing spatial inhomogeneities is this method of growth we developed together with Ziyak Shen and Nick Milosh at Stanford, which we call shallow ion implantation and subsequent overgrowth. And the idea here is to be able to incorporate these impurities at the desired position in lattice, in diamond, with minimal damage to the lattice. Because if you do it the way people normally do it, with very energetic ions, then you damage lattice, and that leads to a large spectral inhomogeneity. So we don't want to do that, which is why we're doing it at very low energies. So we go from 300 kiloelectron volts to 1 kiloelectron volt. And when you do it at 1 kiloelectron volt, then you can easily produce a mask on the chip with electron beam lithography and just do implantation at desired positions, as we do here. But of course, if you do it at low energy, then your ions end up being shallow implanted, close to the surface. So you need to finish everything by growing high purity diamond on top. We've shown that this is possible, and we get the same quality of color centers, same quality of these spin qubits as people do in bulk environment, which is great. And we can actually incorporate them at desired positions, including positions of my group logo, which is not really useful, but shows you that we can really control it. And of course, once you do it on a regular grid, then you can also align your photonic structures in the second level of lithography. And then for spectral control, we developed a variety of tuning techniques, but we're most excited about very simple Stark shifting, which means you put electrodes and then shift your color center transitions by some amount by DC Stark shift. And we've shown in silicon carbide that we can do that without degradation to properties of color centers. We can compensate all of inhomogeneity, and we can also do it in diamond. In diamond, it's a little bit harder because for these color centers, there is only quadratic Stark shift, but we can still compensate pretty much all of the inhomogeneities this way. And that's really those are our tuning knobs. And everybody has tuning knobs. You know, in atomic physics, people also have tweezer arrays, and in other systems, superconducting systems, they also have to tune different qubits and overcome inhomogeneities. But for us, that's really what we're doing to overcome inhomogeneities. And we're confident that these methods now, where they stand in our group and other groups, should lead to scaling to larger sizes of systems than what we've seen so far. So now going back to quantum technologies, you know, apart from just having these optically interface spins that are homogeneous and have good photonic interfaces, you also need photonics, right? Because you need our goal and our idea is to use photons for entangling different spin qubits or entangling different nodes of network or doing quantum simulation or quantum computing on spin qubits. And to do that, we need to build photonics in these materials that are not really conventional photonic materials. And normally people work with silicon. We're here talking about diamond and silicon carbide that people don't really normally use as photonic materials. And when you're building photonics, you need some guiding layer, high index layer on top of some low index layer, as people do in silicon. And you know, for those of you who are younger, you may not know that actually these silicon on insulator wafers that people use for silicon photonics today were commercialized only about 20 years ago. That was 40 years after bulk silicon was first commercialized. And this is really when this whole silicon photonic field took off. And about 10 years ago, people commercialized thin film lithium niobate on insulator. Again, about 20 years after bulk lithium niobate was commercialized. And that's when kind of this lithium niobate photonics field took off, which is very active today. But for silicon carbide, you can only get 6-inch or 4-inch bulk wafers. There is no thin film silicon carbide and insulator. Now, some companies are actually planning to launch it, but as of now, you can't really get it commercially, which is why we had to make it ourselves. And I'll show you in a moment how we're doing it. And for diamond, we also had to figure out how to make guiding structures, which we're actually doing by 3-dimensional bulk carving. So these are some examples of diamond and silicon carbide structures we make. And you can also see all these inverse design elements that are already implemented there. So for diamond, we are actually using 3-dimensional bulk carving, which is literally carving, kind of sculpting in diamond. And that's the method that was pioneered by Paul Barclay from the University of Calgary and was adopted by other groups, including group of Dirk England and Marco Launcher and us. We essentially carve diamond down and then carve it sideways to make these suspended devices. And we've shown that this is also fully compatible with these optimization approaches that I was describing to you before, inverse design. And you can make also quantum photonic interfaces for both silicon and thin color centers. And I already showed you kind of a summary of this, but here you can see a picture of a resonator in diamond with inverse design couplers and high Q with thin vacancy color center, whose emission is enhanced by coupling to the diamond resonator. I guess it's important to do all of that and make photonics in such a way that you are not degrading your spin qubit, which is embedded in the structure. And we've shown that that's all possible. But then for silicon carbide, again, you have to start from bulk material and do something to make photonics. So how do we do that? You know, they tried different things, but the only one that works well to make these pristine high purity films of silicon carbide and insulator was kind of the simplest thing you can think of. You take silicon carbide, you bond it on oxidized silicon, then grind, remove, get rid of most of it, and then etch and polish. And that gives you a thin film of material on top of insulator. We can produce few by few millimeter films, but in principle, it's scalable to larger scales. And we can also do it while preserving properties of all of the color centers. And at the moment, in this silicon carbide material that we produce, we can build Q factors of resonators greater than 5 million. These are, in terms of loss per unit length, better than silicon photonics, even foundry-based silicon photonics, and kind of pretty close to silicon nitride foundry-based photonics, which is the highest quality photonics you can get. So these are some of the structures we made. And again, you also saw inverse design structures. We recently demonstrated also soliton comb, microcomb in this material with comparable threshold to other materials used for soliton combs. And we also recently looked into quantum optical properties of these soliton combs, quantum correlations between different lines in a soliton comb. We built a special instrument in order to do that because we were actually quite excited what happened below the noise level of a traditional optical spectrum analyzer, which people normally don't really do when they work on microcombs. And finally, and kind of most importantly for the quantum part, you can do all of that while still preserving your artificial atoms, your color centers. They're the same pretty much as in bulk material, and they can get also enhanced, their emission can get enhanced by coupling to the cavity, and you can build quantum photonic interfaces. So where do we go from here? I mean, we kind of have, we can overcome inhomogeneities, we can build high quality photonics, both classical and quantum. You can imagine that for building quantum system, you need to have really arrays of these atoms that are somehow communicating via photonic channels so that you can entangle all of these pins. And you will have some sort of electrodes that would control all of them and bring them on resonances with each other, which would be the case in some of the initial experiments. But eventually, as you go to thousands or millions, it will become very hard. So how do you get there? We started exploring something inspired by our inverse design, whether we could kind of simplify this structure and get rid of some electrodes and use fewer electrodes to overcome inhomogeneity. And the idea is kind of simpler. It's really whether we can do the same thing that we're doing in photonic inverse design, which is coupling optimizer and electromagnetic simulator to search through the full parameter space of fabricable structures. But here we would couple open quantum system simulator with optimizer in order to search the full parameter space of driving signals to the system so that we can kind of design control sequences to overcome inhomogeneities. And this is kind of in the space of quantum control, but really relying on optimization. It is different from some of the beautiful work done at the University of Toronto by Alan Asper-Guzik and his team, which is also looking in the context of optimization to design quantum hardware. So far, we've looked into design of driving sequences, but certainly could also do it at the level of permittivities for the system. And we've shown, for example, that for quantum transduction problem, where you're converting a single microwave photon to optical photon, where the efficiency of this problem is limited by the inhomogeneity of this solid state ensemble, you can significantly increase efficiency by applying a single optimized driving signal to the system. And we've shown that we can really improve the efficiency by a factor of about 20 for realistic system parameters, simply by applying single set of electrodes and modulating with this complicated signal, a periodic signal, all of them at the same time, which is recovering their collective behavior. So with that, I'd like to finish and just say that kind of the main message here is, we live at a time where we have excellent computing, classical computing facilities and optimization tools. And we think that relying on these optimization techniques for designing photonic elements is really crucial for building practical systems, because you can build elements that are having better performance, smaller footprints, or are more robust and more scalable. If you're interested in playing with what we've developed so far, you can also download the open source version of our software from GitHub. We've shown that this is fully compatible with Foundry-based fabrication and also very useful for design of quantum systems. It's material agnostic, and we've certainly shown that it could be done in silicon carbide and diamond, but it could also be done in a variety of other materials of your choice. And with that, let me just thank my team at Stanford. This is our current team and also our funding. And thank you all for your attention.